Good morning, friends. Today we discuss about another example for this is fourth unit. In previous video, I discussed about the problem for fifth unit. Here I discussed about the problem for the fourth unit. Okay, we go to the problem. This is ammonia ice plant. The problem is the ammonia ice plant operates between an condenser temperature of 35 degrees Celsius and the operating temperature of minus 15 degrees Celsius. It produces 10 tons of ice per day from water at 30 degrees Celsius to ice at minus 5 degrees Celsius. Assuming simple saturation cycle using only tables of properties for ammonia, determine the capacity of refrigeration plant and the mass flow rate of refrigerant, the discharge temperature, the compressor cylinder diameter and stroke if the volumetric efficiency is 0.65 and the speed of the compressor is 1200 rpm and stroke to bore ratio is 1.2. and the horsepower of the compressor motor if the adiabatic efficiency of the compressor is 0.85 and mechanical efficiency is 0.95 and the theoretical COP of the cycle. Okay, this is the problem. The corresponding TS diagram is this. The refrigerant is ammonia. The lower temperature is minus 15 degrees Celsius and higher saturation temperature is 35 degrees Celsius for the cycle, and the notation points are T1 is equal to T4 is minus 15 degrees Celsius, lower temperature, lower saturation temperature, and T3 is equal to TA, not a T2. T2 is a superheated temperature. Okay, T2 is more than T3. Then T3 equal to TA is 35 degrees Celsius, the second saturation temperature. Then the details for compressor. The compressor efficiency is 0.65 and speed 1200 rpm and ratio between stroke and length diameter is equal to diameter or bore is equal to 1.2 and the adiabatic efficiency is equal to 0.85 and mechanical efficiency is equal to 0.95. Then the ice plant capacity is 10 tons per day, which is equal to 0.115 kg per second from 30 degrees Celsius water to minus 5 degrees Celsius ice. Okay, then first we calculate the capacity of the refrigeration plant from the ice produced from minus 30 degrees Celsius water to minus 5 degrees Celsius ice conversion. Okay, then the formula is refrigeration capacity is equal to mass flow rate of ice into sensible cooling from 30 degrees Celsius water to 0 degrees Celsius water plus latent cooling from 0 degrees Celsius water to 0 degrees Celsius ice, then plus sensible cooling from 0 degrees Celsius ice to minus 5 degrees Celsius ice. This is the formula for the capacity of refrigeration plant from the conversion of ice from water. Then the assumed values are the Cp of water is equal to 4.186 and Cp of ice equal to 1.94 kJ per kg Kelvin and latent heat of cooling nothing but enthalpy of fusion which is equal to 335 kilojoules per kg. Those are the constant values for water. Then substitute all values and calculate the refrigeration capacity which is equal to 54.43 kilowatts. Then from the tables for ammonia, the refrigerant tables, take the values of enthalpy at 0.1 and entropy at 0.1 and enthalpy at 0.3 which is equal to enthalpy at 0.4. Therefore, because the process is isenthalpic process between 3 to 4 and also S1 equal to S2 because the compression is isentropic. Then the specific refrigeration capacity from that formula, specific means per mass basis. Then the QE equal to H1 minus H4 which is equal to 1077 0.8 kilojoule per kg. From that we calculate the mass flow rate of refrigerant, which is ammonia. Is equal to whole replacement capacity, which is 54.43 kilowatt, and the specific replacement capacity is equal to 1077.80, which is equal to, which gives 0.0505 kilogram per seconds of ammonia mass flow rate. Then we have calculated the enthalpy at point 2. It's a difficult one because the point is in the superheated region. Then first we calculate the superheated temperature of a particular point, and with the help of that particular temperature we can calculate the enthalpy value. The detailed procedure is as follows. From the table, entropy and enthalpy of vapor saturated at 35 degrees Celsius and superheated by 50 degrees Celsius and 100 degrees Celsius respectively. The data's value from the superheated table of ammonia. Sg is equal to the Sg at 35 degrees Celsius, which is 5.2086, which is less than S1 or S2. Therefore the condition is superheated. That means T saturation 2 is less than T superheated. Then we go to the interpolation calculation to find the T2 or T superheated value. You need not write the all things in your examination. This is for the explanation purpose only. Okay, then the interpolation calculation is from the superheated ammonia table. Entropy value of 5.646 is at 50 degrees Celsius, and entropy value of 5.9806, the temperature is 100 degrees Celsius, and the entropy value is 5.8223, what the temperature of T2. T2 is unknown value. Then the interpolation formula is this: y minus y1 is equal to y2 minus y1 divided by x2 minus x1 into x minus x1. Here y is a temperature value and x is a entropy value, which means y is unknown, x is known. Then substitute the values, calculate the temperature, which is equal to 76.30 Celsius, which is the temperature at point 2. Then we have to calculate the H2 with the same procedure. From superheated ammonia table, the temperature and enthalpy is taken. Here at 50 degrees Celsius the enthalpy value is this, and at 100 degrees Celsius the enthalpy value is this, and the temperature is 76.30. What the enthalpy value? Then substitute the similar formula seen in the previous case. Then calculate the H2, which is equal to 1670.10 kilojoule per kg. Okay, that the task is completed. Then the another calculation, piston displacement of compressor. This discharge formula is ALN by 60. A is nothing but area, therefore the area of the cylinder, that is cross sectional area of the cylinder, that is pi by 4 d square. D is a bore diameter, L is stroke length, which is equal to discharge mass flow rate of ammonia into specific volume divided by volumetric efficiency of the compressor. Then the small v1 is specific volume of ammonia at minus 15 degrees Celsius. Then this value is taken from the ammonia table. Here which is equal to 0.599 meter cube per kg. Then the substitute the all values. Already we know the length is equal to stroke length is equal to 1.2 of bore. Then the conversion then in the formula we have divided by 60, which is the conversion factor from minute to seconds. With the help of from this calculation we have found diameter is equal to 0.128 meter and length is equal to 1.2 d is equal to 0.154 meters. Then power consumption. The power consumption from the compressor formula is equal to mass of ammonia into H2 minus H1 divided by adiabatic efficiency and mechanical efficiency. If adiabatic efficiency and mechanical efficiency are not given, then the formula is become numerator only. Then substitute the values. We have 14.14 kilowatts. In terms of horsepower, 1 kilowatt, 1 HP. The conversion factor is 1 kilowatt is equal to 0.746 sorry 1 HP equal to 0.746 kilowatts. With the help of conversion we have 18.96 HP. Then the last value, last findings, the theoretical COP. The formula for this theoretical COP is H1 minus H4 divided by H2 minus H1. Then the H1 minus H4 is already calculated, which is for specific refrigeration capacity, and substitute the H2 and H1 value, which is nothing but compressor work. It's also specific. The value is 4.767 we get. Then the actual COP means from the actual COP is calculated from the refrigerant capacity with the help of ice plant, which means ice is produced from water. Then the compressor work, then the value is 3.77. Then the actual COP is less than the theoretical COP by 1. With the help of this problem you can solve the remaining tutorial problem uploaded in the classroom. Thank you.